Uh, Hello, everyone. Welcome to the second lecture on gravitational waves from Professor Ajith. Whenever you want to start, Professor.
Okay, thank you, Esteban. For those of you who were there in the past lecture, we gave a broad introduction to gravitational waves and how to derive the phenomenon called gravitational waves from linearizing Einstein's equations. And we also did a broad overview of the astrophysical sources of gravitational waves. So today my plan is to ask how one could possibly detect these gravitational waves passing through the Earth. And I will be focusing on one particular technique, which has been the most successful so far, which is using large interferometers. I will also give you a flavor of once we have data from such interferometer, how one could extract signals that are deeply buried in the noise, and also once you detect these signals, how one would extract the astrophysical properties of these sources from these observed signals. That is a plan for today. And tomorrow I will give you a broad overview of the current status of these gravitational observations using LIGO, Virgo, and Kagra, and give you a glimpse of what is awaited in the near future. So first part is the detection of gravitational waves using interferometry. So this first equation is something that we derived in the first lecture. So we showed that in the inappropriate gauge, which is called the transverse traceless coordinate system, transverse traceless gauge, gravitational waves, the metric perturbation that is perturbing on the Minkowski metric, has only two independent components. So in this case, the wave is traveling along the z direction, and the wave is transverse, so it has non-zero components only in the xy plane. And even in the xy plane, because of the tracelessness condition, the xx and yy components are related. Yy is actually minus xx, and this xx is called, for simplicity of notation, h plus. And the reason for that notation, I will make it clear in 1 minute. And the other component, xy or yx component, because symmetry, they're the same, and they're called h cross. Now, let's take a look at how such a perturbation over the Minkowski metric would change the proper separation between points, which is something that we aspire to measure using these interferometers. So here, the gravitational waves in this gauge can be written as a time-dependent perturbation to the spatial part of the Minkowski metric. So if you have originally two particles which are separated by a distance of 2x in the x direction of your coordinate system, essentially the gravitational waves, in the presence of a gravitational wave, the metric will be basically 1 plus h plus. That would be the metric. And then if you were to compute the proper distance between the 2 points, it would become 1 plus h plus to the square root. And because it's a weak perturbation, one could write this 1 plus h plus by 2. So basically, it would add, you basically have these, the gravitational wave perturbation would basically add a small increment to the proper distance between 2 points. So originally, when it was dx, now the proper distance between 2 points that were originally separated by a distance of dx will be changed to 1 plus h plus by 2 by 2. Similarly, the same gravitational wave would change the proper distance between the 2 points separated by an original separation of dy in the y direction will change by 1 minus h plus by 2. This is the second one is a typo. It should be minus. So again, this is 1 minus h plus to the power to the square root. So if you expand it, it becomes 1 minus h plus by 2. I apologize for the typo. It has to be 1 minus h plus by 2. And this is shown in this animation here. You have a ring of test particles that are free to move. They are freely falling particles. And when a gravitational wave passes, and these are in the XY plane, and when a gravitational wave passes through perpendicular to this plane along the Z direction, during a time of a positive H plus, the X direction will get stretched. At the same time, the Y direction gets compressed because it becomes 1 minus H plus by 2. And in the next half cycle, when the sign of the gravitational wave change, the X direction will get compressed and the Y direction get extended. And basically this ring of test particles, which are originally arranged as a circle in the absence of any perturbation, will get deformed into ellipses like this. And if you now look at the effect of this other polarization, the cross polarization, the effect is very similar, except that the axis of deformation is shifted by an angle of 45 degrees. So that's why it's called it has a cross type signal, while this has a plus kind of shape. So this is what one would hope to detect using these interferometers. Here's another animation how these gravitational waves are propagating through space and how it is basically disturbing the spatial metric, the component of the spatial metric perpendicular to that, and has changing the proper distance between points that are perpendicular in a plane perpendicular to the direction of propagation. So you can see that each circle is deformed into ellipses like this, and these propagations propagate, and these are the gravitational waves. Now, a simple way of detecting these deformations is using an interferometer. So here is a simple Michelson interferometer. You have a laser source here, which is split into two orthogonal directions using a beam splitter. And half of this get reflected like this, and half get transmitted. And you have two end mirrors that reflect the light back. And you can configure these interferometer distances such that this interference of these reflected beams is destructive, so that there is no light leaked into this, what is called a dark port. And here is a photo detector that is recording any reflected light. Now, when you have a gravitational wave going perpendicular to this, as we see in this previous slide, as we saw in the previous slide, the X direction get extended, and at the same time, the Y direction get contracted, the same cycle. And if that deformation is delta L, basically, you can compute the amount of deformation that is caused by a metric perturbation of H, and it turns out to be delta L by L, where L is the original separation of these test masses. For example, here the beam splitter and this mirror is acting as a test mass. So if they are originally separated by about a distance of L, the corresponding change in this arm length is L times H. And even for so you can see that this is like acting like a strain, right? If you have a longer arm, basically the same gravitational signal can create a larger strain, a larger differential change. So this delta L by L is like a strain. So the gravitation is actually producing a strain on the interferometer. So the interferometer is a very standard technique. It's been around for over 100 years. But the difficulty here is that the expected displacements expected to be produced by standard realistic astrophysical signals is extremely weak. It is order 10 to the minus 18 meter, even if you have a kilometer size instrument. So that the delta L by L is order 21 or even smaller now. So that's why it is a challenge. So why is it a challenge? You could, if you remember your undergraduate interferometry, you would remember that the typical distance that you can measure, typical differential changes in the arm length that you can measure using a simple Michelson interferometer is order the wavelength of the light used. So what is the typical strain that a simple interferometer can measure, like in a tabletop interferometer? So the strain is delta L by L, and the delta L that you can measure using a typical tabletop interferometer is order the wavelength of the laser, which if you have an infrared laser or optical laser, it has a wavelength of something like 10 to the minus 6 meter, a micrometer. And even if you have a kilometer size instrument, if the L is 10 to the 3 meters, then the strain that you can measure is order 10 to the minus 9. And you might have seen that the strain that LIGO is measuring, LIGO and Virgo are measuring, is order 10 to the minus 13, 23 or 24. So how is it possible at all? So how can we improve the sensitivity of these instruments? One is that you can increase the effective arm length of the interferometer by bouncing the light a number of times, let's say 1,000 times. So by bouncing the light in the arm by about 1,000 times, you can increase the effective arm length by a factor of 1,000. So that will give you another factor of 1,000 in your strain sensitivity. So that will give you about 10 to the minus 12. Still far from what we want to do. But now, in a standard, tabletop interferometer, you are measuring a full fringe shift. But there is nothing fundamental that is stopping us from measuring a fractional fringe width. So for example, if you can measure how the intensity of light changes from the full bright to full dark port, if you can measure a fraction of this change, then you can do sub-fringe interferometry. But here there is actually a fundamental limit, which is that you only have a finite number of photons that are used for this measurement. And these photons are, they are quantum mechanical particles, and they obey certain statistics, and they have a short noise. They come with a particular Poisson distribution in their arrival times. And even if you have an average number of photons, if you have a laser with a given intensity, let's say 1 watt, it is an average power that is created by the laser. At a given time, there are number fluctuations in the number of photon, that is order square root of n. If your average power is, if you have for a given laser power and a given frequency, if you have n photons on average, then the fluctuations in the statistics of these photons is order n to the square root. So and we want to measure, we are able to measure only changes that are larger than this intrinsic fluctuations in the number of photons. So that has to be basically order. So basically it is the delta L that you can measure is something like lambda divided by square root of n. And you can do a calculation and show that if you have a laser power of about 1 watt and a laser of 1 micrometer, and if you have a 300 hertz of gravitational waves, basically you can collect about 10 to the 16 photon. So the delta L that you can measure is lambda divided by about 10 to the 8. So we are now getting to more realistic numbers. With this kind of watts of laser power, we will be getting closer to the regimes of where we can actually make astrophysical measurements, which is order 10 to the minus 20. But in now realistic interferometers, we have several kilowatts of laser power, even though the original laser has only about 20 watts or 10 watts. Using techniques, creating like resonant cavities and recycling the laser power using techniques like power recycling, these arms of this interferometer have several kilowatts of laser power. And that's why we are able to do this sub-fringe interferometry and go up to sensitivities of order 10 to the minus 23 or even better. So that is why we are able to make these measurements. So how can one do this? Do these things? One is, for example, so if you are able to achieve this kind of tricks, for example, increase the effective arm length of the interferometer by a factor of 1,000 or so, and create a large laser power so that we can reduce now the counting statistics of photons. We can achieve these sensitivities. And how does one do that? One is that to increase the effective bandwidth, there are two methods. One is that you basically reflect the light backwards and forwards using what is called the delay lines, where they don't basically interfere. For example, the geo interferometer in Germany uses a technique like this, but it has additional complications. But the most popular technique that is used by all the large interferometers is like LIGO and Virgo, is to create resonant, what is called a Fabry-Perot cavities. So you basically tuned the length of these mirrors such that the light is basically resonantly amplified, and you create a resonant cavity in which the light is circulated for a long time. And that is the most popular technique used, and this way you can increase the effective bandwidth by order 100 times or even larger. So even this one, so now even if you do that, there are a number of noise sources that affect. There are a number of fundamental noise sources that would affect our measurements. One is the one that I mentioned, the fact that we have only a finite number of photons to count, and this is called the photon short noise. And this basically affects measurements of very short time scales, because you have to count the number of photons in a short time scale, and that's where the error is larger, which means that it affects the sensitivity of the interferometer at higher frequencies. And you can improve this error by increasing the laser power, because this error is, is like proportional to 1 over square root of n, which is the number of photons. But it turns out that if you improve the short noise by increasing the laser power, it actually increases the other side of the noise spectrum, because it creates additional kind of noise, which is called the radiation pressure noise. Basically, these are, you're doing a very precise measurement, and you have a large pressure which is caused by the photons that are hitting this mirror, and it is actually moving the mirror. And it's called the radiation pressure noise. And it turns out that the radiation pressure noise is actually proportional to the square root of the number of photons, while the short noise is inversely proportional to the square of photons, the number of photons. So if you increase the laser power, it actually improves the short noise, but it increases the radiation pressure noise. So if you increase the laser power, it improves the high frequency sensitivity like this, but it actually makes the low frequency sensitivity worse. There is a compensation, there is a balance between them, and there is a fundamental limit called the standard quantum limit, which is where this sort of knee of these two different noises actually change as a function of the radiation, so the laser power. But there are actually ways of going around the quantum limit, the standard quantum limit, using techniques like a squeezed state of the vacuum. I won't talk about that. There are also other sources of noise. One is that the seismic noise of the Earth actually create mechanical vibrations on the mirrors, and this has typically an inverse power law. It dampens at higher frequencies with some index which is order at 2. It suppresses high frequencies, and there are actually ways of suppressing it for frequencies above about 1 hertz by suspending all these optics like mirrors and beam splitter, etc., as pendulums of multiple stages. So if you have a simple pendulum well above the resonant frequency, these noises are suppressed by a factor of f to the 2, or 1 over f to the 2. And if you have a pendulum system of several stages, each stage will suppress the high frequency oscillations by a factor of f to the minus 2. So then LIGO has triple stage pendulums, and which will significantly dampen the oscillations. And Virgo has an even fancier seismic isolation system called the super attenuator. On top of that, LIGO also has an active noise cancelling mechanism, so similar to how the noise cancellation headphones work. You basically measure the seismic noise using a number of seismometers, and basically you move the base of these mirrors or the suspensions in which these mirrors are suspended, so that you compensate for the motion of the Earth. And this works well for the very low frequency oscillations due to the seismic motion. So the seismic motion affect the lowest frequency part of this one. In the intermediate part of about 100 hertz, where LIGO has the best sensitivity, the noise budget is dominated a few hundred hertz. The noise budget is dominated by thermal noise of the mirrors, as well as the suspensions that are used to suspend these mirrors. Basically, this is because all these are in some finite temperature, and there are various thermal fluctuations that are on the substrate of the mirror, as well as the coatings that are used to reduce the absorptivity of these mirrors. And these thermal noise of both the mirror as well as the coating as well as suspensions cause thermal noise, which is also a limiting noise at these intermediate frequencies. And the way to deal with this is, you basically identify materials just some very high quality factor, so that all these thermal vibrations are limited to some very narrow frequency band, which we don't care. We can limit the noise in which. Okay, so to summarize, this is like the advanced interferometers, like advanced LIGO, basically use all these technologies to do this very precise measurements. So, for example, they are kilometer size Michaels interferometers with Fabry-Perot arm cavities, and they use some extremely high quality optics to minimize the motion of the test masses due to thermal noise. And to minimize the coupling of the seismic noise, they are suspended as triple pendulums with an active part, as active seismic isolation part. They use some very highly stabilized lasers to produce highly stable frequency of the light. And the entire system is in some extremely high vacuum to minimize scattering even by a small number of atoms of air in this tubes. So here is an image of the power spectral density or the amplitude spectral density of the noise in the LIGO system. So basically, this is a Fourier transform of the noise that is averaged over several cycles, and it gets an estimate of the measurement uncertainty. This means that, for example, the measurement is the most accurate between about 10 hertz to about 1 kilohertz. And below 10 hertz, the noise goes up very steeply because of the seismic motion and other contributions, like the radiation pressure noise and the what is called the gravity gradient noise, because of the Newtonian fluctuations in the gravitational field of the Earth. And at high frequencies, it is predominantly dominated by the photon shot noise. And at this intermediate frequencies, it is dominated by the various thermal noises. So that and use one can make the instrumental scientists of LIGO and Virgo have a pretty good understanding of where the limiting noise sources are, except for some part of technical noises also. So that's just my quick summary of the gravitational wave detection using interferometry. So before I proceed to the part where I discuss the data analysis aspect, are there any questions?
No, I don't see any questions so far.
Okay. So let's go ahead. So now the problem is that we have some astrophysical signals that are mostly buried in the noise that we see here. So how do we detect these signals? And we want to make this detection methods as optimal as possible, because we want to detect even the weakest signal that there is in the data. So now let's have some a brief intro of random processes and how to characterize them using various moments of their distribution. Basically, a noise is basically a random process. So if basically these interferometers record the intensity of the light that is coming out of these photodiode, which is converted to electric signal. It's digitized, and basically we are looking at these digitized samples of these light. And after calibrating it, it gives you a measure of the gravitational wave induced strain of the on the detector. So you have some sort of a time series data where you have a strain, which is plus some noise as a function of time, and this is dominated by the noise in the interferometer, and which can be thought of as a sequence of random variables x, which is a function of time. And this is the data. And even though it's impossible to know the exact realization of this noise, because you have a large number of random variables which form, even if it's follow from distribution, it's impossible to predict what is a particular realization of the sequence. Even though it's impossible to do that, one can get some reasonable estimates of the statistical property of the noise. For example, one could estimate its mean, one could estimate its variance, and one could estimate its higher order moments, etc., etc. And you know how to compute these higher order, basically various moments of distribution. If x is following some probability distribution px, then the first moment is the mean. So thanks, and it's basically x times p of x integrated over the value of x, and this is called the ensemble average. Now, and we basically invoke the property of ergodicity, and this can be invoked if this process is like a stationary process, then which means that basically the statistical properties of the sequence is basically unchanged over different times. In that case, these ensemble averages can be replaced by time averages. So from here, you can estimate from here. So basically, the mean is x of t dt, and integrate from over a long time and divide by 1 over capital T. And if this noise is stationary, then essentially it turns out that this autocorrelation function, which is basically the ensemble average of x of t with x of t plus some tau, depends only on this tau, the time shift between these two. So it shows how different samples of a noise process are correlated with each other. And it is characterized by this autocorrelation function. Now, the simplest kind of noise that we can imagine is the white noise, where basically all these samples of noise are independent of each other, which means that the autocorrelation function is non-zero only when the time shift tau is 0. So if you do in one time shift and integrate it, basically there is no correlation between them. And here is a cartoon that shows how the autocorrelation function of the times of the white noise would look like. It has a large value at time shift of tau of 0, but for any non-zero time shift, the value is very, very close to 0. And if you take a Fourier transform of this autocorrelation function, it is called the power spectrum, and this is shown in the white in the right side. And the power spectrum is flat, and that's why it is called a white noise, because if you take the analogy with light, the light has basically equal components of color from various frequencies, and that's why it appears to be white. And in this analogy, if the noise has equal components, equal contribution from different frequencies, it's called white noise. It is independent of the Fourier frequency. It has a flat spectrum. In practice, the observed measured noise in any instrument most instruments are not white, because this noise is produced by some very complicated processes. So here is, for example, the autocorrelation function of the LIGO data from a few years ago. And you can say it's not white. There is some correlation between them. There's some shape. And if you take a Fourier transform of that, you get this kind of a shape, which is the shape that we saw earlier. So this is basically the power spectrum in fact, the square root of the power spectrum of the LIGO noise. So it has some higher noise part and lower noise part. And this means that you better do your measurements in this range where you have the best sensitivity, which is about 100 hertz or so. Okay, that was just a prelude of the random processes. Now, if we assume that the noise is, to a good approximation, stationary Gaussian, which is true to a good approximation, then it turns out that the properties of the noise, the statistical property of the noise, are entirely determined by just the two moments of distribution, which is the mean and the variance. And mean we can actually ignore because most of the time the mean is 0. But even if it's non-zero, we can compute the mean and subtract the mean from the data so that you have a zero mean Gaussian process. So this means that the only thing that we care about is the variance of the distribution. So if we have the variance distribution, we can actually compute the probability of observing a given sequence of random variables. And that is given by this multivariate Gaussian distribution. So if xj are different random variables are drawn from a Gaussian distribution of mean 0 and variance sigma square, the probability of observing a particular sequence of these variables, the set xj, is given by basically this, where you multiply the probability of observing each random variable. So that you're going to multiply, but then you can take this in the inside, that multiplication to this inside is exponential, and that becomes a sum. So this is basically the probability distribution for observing a sequence of random variables xj. And this is in the discrete limit, and assuming that the noise is white. And you can make the continuous limit of that by replacing these sum by an integral, and it is basically the same thing. This becomes, and you can write this in terms of the Fourier transform. So you can write this into the Fourier transform of the noise xf square divided by the power spectrum, which is basically the variance in this way. Now, you can also show that even if the noise is not white, it has a color, which is represented by something like this, which is described by a frequency-dependent power spectral density, S of f. You can actually divide the Fourier transform square divided by the corresponding power spectral density and compute the probability distribution of a particular sequence of noise. So the same form would work for colored noise also. So in summary, if you assume that the noise is Gaussian and if we can measure its power spectral density, we can compute the expected probability distribution for a given sequence of the observed data. It is given by this one. And so, and you can see that this has a particular form. It is basically the absolute square of the Fourier transform of the data. So if you write, for convenience of the notation, if you introduce this, it's basically, if you think of this, what you see on this left-hand side, the right-hand side, is basically an inner product between here y and y, right? So if you define some kind of inner product like this, if you define inner product between the vector A and vector B as the product of the Fourier transform of A and B's complex conjugate, it is inversely weighted by the power spectral density and integrated over the standard definition of the inner product, then you can write this P of x or t in this very compact form. It is exponential minus inner product of x and x divided by 2. So to summarize, if you measured a sequence of random variables x, the probability, you can compute the probability of getting that random variable from your data by computing this this inner product between x and x, and that is given by that. Now, so keep this in mind. And now we are going to see how one could use this to construct an optimal method for detecting non-signals in the data. So in any case, if you have a signal in noise, one cannot for sure say that we have detected a signal. One cannot say with absolute certainty that we have detected a signal. One can only make a statistical statement. There is always a probability that we will be wrong. So essentially what we are asking is that given you have some data, S, we want to compute some kind of a ratio of probabilities. The probability that you have two hypotheses. One is that this data S contains a signal, which is called the H1. and which means that this S of t contains some noise plus some signal, and our null hypothesis, which is that the data contains only noise. So that's the null hypothesis is that basically the data is just purely noise. And the signal hypothesis, or the alternative hypothesis, H1, is that the data contains a signal plus noise. So from this observed data S, we want to compute the ratio of the posterior probabilities of these two hypotheses. Posterior probability is a conditional probability that after, given that you have observed this data S. So you want to compute odds ratio. You have to compute the ratio of two odds, the odds of H1 being true to the H0 being true, right? So how do we do that? So we have this good old Bayes theorem, which actually tells you that the posterior distribution of this variable H1 given data can be split into a product of the prior distribution of H1 times the probability of S being true times H1, which is given H1. So, or the likelihood of S1 given H1. So if you have not seen the Bayes theorem before, it is something that one could very easily derive from the definition of joint distributions. And you could look up Wikipedia or any textbook. And basically, so this allows you to write this posterior probability as a product of the prior probability of the hypothesis times the likelihood of the data given H1 is true. So you can split both hypotheses in the same way and factor these. So here, this is a ratio of the prior odds of the two hypotheses. What is our understanding of the high H1 being true versus H0 being true before we looked at the data? And this is the part of the data that depends on the data. This is part of the odds ratio that depends on the data. This is called the likelihood ratio. So given H1, what is the probability of S? And given H0, what's the probability of S? The ratio between these two likelihoods is called the likelihood ratio or the Bayes factor. Right. So our aim is to compute this likelihood ratio from the data. So basically, remember it's P of S1, S given H1 and P of S given H0. Now, what is P of S given H0? Which is basically asking, if your data contains only noise, what is the distribution of that? It's something we have derived just earlier. We used X before, and it is basically exponential minus the inner product of S with S itself divided by 2. So that is the probability, the likelihood of the data being just pure noise, or the likelihood of the null hypothesis. Now, what is the probability of H1, or what is the likelihood of H1? Basically, we are asking whether the data contains some signal H of t, or we are asking if what is the distribution of S minus H. So if that is the case, if the data contains an H signal H, then S minus H should be equal to N, which is just a noise, right? Because the S is N plus H, and we are asking what is the distribution of S minus H, which is the same as the distribution of N. And basically, we can say that distribution of S minus H is basically exponential of minus inner product of S minus H and S minus H divided by 2. So we have written down the likelihood of H0 and the likelihood of H1. And the likelihood ratio is between the ratio between these two. And so it's S minus H, S minus H. So you have, if you expand this, you have terms SS, HH, and 2SH. And since this denominator also has an SS term, that would cancel out. So you remain only the two terms in the numerator remains. One is H and H, and another is S and H. Now, what is the part that actually depends on the data S? Only this part depends on data. And this particular part, the HH, acts like a normalization. So basically, the likelihood ratio just depends on this likelihood, this inner product S and H. So the likelihood ratio is basically a monotonic function of the inner product of the data with the signal model H. So if you want to detect some signal that is H that is buried in some stationary Gaussian noise, your optimal method is basically computing an inner product between S and a copy of H or a template of H. And this is called the match filter. And the inner product of H is basically in the time domain a cross correlation function, because there is a theorem in Fourier analysis that shows that the Fourier transform of the cross correlation is basically this inner product that we defined earlier. So in summary, we have shown that if you have a non-type of signal that is buried in stationary Gaussian noise, you can compute the likelihood ratio based on this inner product between data and signal, which is called the match filter. But now the question is, we don't actually know what is the signal that is buried in the data. We have to find that out. So how do we do that? 1 second. So even though we don't know the exact signal that is buried in the data, we have in our mind some class of signal that we want to look for. For example, we want to look for gravitational signals from coalescing compact binaries of black holes and neutron stars. And we have at least illustrated some way of computing how gravitational waves can be computed from these signals, these sources. And once you have, then, of course, the signal shape actually depends on the properties of the source, such as their mass of the black hole, their spin angular momenta, their location, etc., etc. So the signal shapes are functions of the parameters of the source. But then one can actually, introduce a parameter in your hypothesis. So your hypothesis H1 has a parameter lambda, which basically means in this case properties of the black holes, their distances, etc., etc. And once you introduce the parameter, you can invoke some prior distribution of these parameters and marginalize your likelihood over those parameters. Again, it's a very standard process, method in Bayesian analysis. So basically, one has to do an integral. So one has to write down this expression of the marginalization. So this hypothesis has a parameter lambda, and you introduce some prior on this parameter, and you marginalize over lambda. In practice, doing this integral is computationally very expensive. It's an n-dimensional integral because typically the parameter space of the binary black holes is a very large dimensional parameter space, like 16 dimension. So to do an integral of this likelihood in 16 dimensions is very expensive. So one cannot do it as regularly as part of a search. So, however, if this likelihood ratio has if the likelihood ratio is well peaked, has a narrowly peaked, has some narrowly peaked shape, then it turns out that one can kind of approximate this integral, and we can, instead of marginalizing this likelihood, one could maximize it. One could just look at the peak of the likelihood over the parameter space of lambda. So basically, this is equivalent to maximizing this inner product between the data and this template of the signal, a model of the template, which is parameterized by this and a set of parameters lambda over the entire parameter space or parameter vector. So this is called the maximum likelihood method. So you basically maximize the likelihood over the parameter space that we are interested in. Now, what is a parameter space? For example, for the most popular kind of sources that we are interested in. And these are binary systems of compact objects that we encountered. These are parameterized by the mass of two black holes, and each black holes have their independent spin angular momentum. They are each three-dimensional vectors, and you have to have three coordinates to describe the location of the source in the space. And it turns out that you have to have two angles describing the orientation of the binary. and a third angle describing the reference phase. So basically 3 Euler angles that relate the coordinate system in which the binary can be computed as opposed to the coordinate system in which the detector is located. And on top of there is some arrival time. So there is some 60-dimensional parameter space that you have to work with. And basically, you have to maximize your likelihood over this 16-dimensional parameter space. So is it 16, like 2, 8? That is and 11, 13. Okay, 15-dimensional parameter space. So again, there are more parameters that one could do, like the eccentricity of the orbit, etc. This is 15-dimensional parameter space. And it turns out that there are some clever tricks that can use to maximize the likelihood over certain parameters. For example, to maximize your likelihood over the distance and orientation angles, etc. One could write down all these angles in terms of two effective parameters. One is an effective amplitude of signal and an effective phase. And there is a nice way of maximizing your signal noise ratio or maximizing your likelihood over these 2 parameters. And to maximize this, the likelihood ratio or this inner product over a time shift or a time of arrival of signal, one could do a trick using Fourier transforms, which is basically computing the correlation function using a fast Fourier transform. And here is an illustration of that. So here is the middle plot shows some noisy data in which we have buried a signal like this, a blue signal, and it is actually there, but we cannot see it. But if you compute a cross correlation between the data and the template, you get a certain peak here. So that will show you that where exactly is the signal located in the data. So if you put the signal at time 0, you get a cross correlation. And this can be computed rather inexpensively using what I call the fast Fourier transform algorithms. So one could do it in a computationally inexpensive way. So the remaining things that we don't know how to maximize are these intrinsic parameters, so the masses as well as the spins of these black holes, etc. So we have no clever tricks for maximizing the likelihood over this intrinsic parameter space. So one needs to do a brute force. So what one does is to create a catalog of templates or a bank of templates corresponding to different values of the black holes, masses, their spins, etc. There are order like millions of them. And you cross-correlate the data with each of these templates. And here is one example of a template bank that is used by one of the first observing runs in LIGO and Virgo. That shows the horizontal axis is the mass of the primary object in the binary, and the vertical axis shows the mass of the secondary object in the binary. For example, if these 2 objects have mass less than about 2 solar mass, then they are more likely to be double neutron stars. And if they are if they have masses, both of them have masses or greater than about 3 solar masses, so they are more likely to be double black holes. And in this regime of one being a light object, other being a heavy object, then they are likely to be a neutron star black hole binary. And each dot here basically corresponds to one waveform template that is used to match with the data. So there are a few 100,000 templates in this plot, but in the current template bank, there are a couple of million templates. So one has to do this correlation with each of these million templates. And so then you can get some value for this match filter statistic or the likelihood ratio and compute some signal to noise ratio of this estimator. But so even if you get some value, the question is, what value is good enough? What value of signal to noise ratio is actually good enough to claim that we have detected a signal? Because if I come back now, if you remember what I said in the very early of this in this lecture, when you are making an inference in the presence of noise, one cannot be absolutely certain. There is always a small probability that a particular realization of the noise would mimic a signal. It's very small, but there is a probability. And this is called the false alarm probability. So you could ask, if you have pure noise, right, and compute your detection statistic, which is basically the inner product of the data with the template, what is the distribution of that statistic? And here's a cartoon that shows the distribution of the such detection statistic when the data contains entirely the noise only. So on average, we expect that these detection statistic will take only small values. So it has values like this. While on the other hand, even if you have a true signal the data, we expect that the statistic would typically take higher values because you will have a larger inner product with this template. However, the noise can still kind of anti-correlate or or basically downweight the correlation, and the inner product, it can drive this inner product into very small values also, even though the probability is very small. So here is the distribution of the signal, this detection statistic when the data contains signal plus noise. So you can see that there is an overlap between these two signal to this distribution, which is actually a confusion regime. So what one does is to choose some kind of a threshold such that the probability for a noise to produce values above this threshold is small, like 1 in 1 million or something. And this would automatically imply that you have some false dismissals also. You have some loss of efficiency because so this false alarms is shown by this dark region, which is basically integral of this distribution of the noise-only triggers, noise-only events. It's above this threshold value. And the false dismissal probability is shown by these hatched region. It's basically the integral of this distribution of the signal plus noise statistic from minus infinity to or 0 to this statistic value. So a choice of a particular threshold introduces two kinds of errors. One is called the false alarm. Sometimes a fake signal can be claimed as a true signal, and a false dismissal where a true signal can be dismissed saying that it's a noise trigger. So we cannot avoid this kind of errors. And a good detection statistic basically maximize your in fact, minimize both errors. It basically minimizes the false dismissal probability for a given choice of false alarm probability. So that's how you make a detection of a signal. So let me skip these few things and come back to this a bit later. Okay, no, I'll continue this. So one can actually, so with some confidence, one can make a detection of the signal. And once you made a detection of a gravitational signal with some confidence, we have to do better. We have to infer the property of the source from this observed signal. And here, one is actually interested in all the properties, such as the distance, location of the source in the sky, their masses, their spin angular momentum, etc. So one should not do like a reduction of this parameter space as we did for the detection problem. So one basically have to do a parameter estimation or have to compute the likelihood in this n-dimensional, 15-dimensional parameter space. So one is actually interested in asking the question, given that we have observed the data S and assuming some hypothesis on the nature of the signal, that, for example, this is a signal produced by a compact binary merger, which is described by general relativity. That's our hypothesis. If you have that hypothesis, can you compute a distribution, a posterior distribution of the properties of the source? And this theta vector involves things like masses, the spin angular momentum of the black holes, distance to the source, their location in the sky, orientation of the binary, etc., etc., etc. So one again can use the Bayes theorem and write this posterior as a product of this prior distribution of these parameters times the likelihood, and it is normalized by the integral of this denominator, which is called the evidence. And this evidence, you can see that it's a function of the data and the hypothesis only. So it's an evidence of this hypothesis. And if you have multiple hypotheses, you can rank these also. I'll come back to that later. But for the time being, this denominator is just a normalization constant, which makes sure that the left-hand side is a probability, actually, a probability density. It integrates to 1. And so from the data, one needs to compute this likelihood, the likelihood of observing a particular data S given the hypothesis H and a set of parameters theta. And since we are now dealing with a 15-dimensional parameter space, one cannot compute this on a grid because you need to a large number of computations. So instead, one rely on some sort of a stochastic sampling technique, just the Markov chain Monte Carlo. So basically, one using a stochastic sampling method like a Markov chain Monte Carlo, one basically computes samples from this posterior distribution. And often, we are interested in, if you're interested in one set of parameters, let's say the mass of the 2 black holes, we can marginalize over these other dimensions, which can be done simply using a histogram and compute a distribution of these marginalized distributions of these 2 parameters. This, for example, shows the marginalized distributions of the masses of the black holes observed from the first gravitational signal. So, for example, with 50% probability, we can say that the masses are lying in this region. While if you want to increase the confidence, basically the uncertainty actually increases like this. So that's about parameter estimation. And there are a bunch of issues here. For example, I glossed upon the statement that one has to choose a set of priors. One has to choose a prior distribution of theta. Sometimes it's obvious, for example, the prior distribution on the location of the source in the sky. So if you invoke that the universe has no preferred directions, there is isotropy in space, then, and as long as you can see sufficiently far away into the universe, the right distribution for the sky location that the sources has to be distributed uniformly in the sphere. So there are some obviously right priors. However, on some other parameters, so the mass distribution of black holes, we do not know what the right prior is because it's the first time we are seeing this kind of black holes. So one has to start with some assumption of the priors. Let's say, assume that the prior is flat. There is equal likelihood of finding black holes of all masses in the universe. So if we start with the prior, we get some posteriors. And once we build our understanding of the universe, then we can actually feed back these posteriors as priors for future measurements. And as long as this likelihood is very well localized, as long as signals are strong, choice of priors does not matter a lot. However, when the signal is very weak, then the priors actually matter a lot. One example is our measurement of the spin of these black holes that we observe from gravitational observations. It turns out that the spins have a very, very weak imprint on the observed gravitational wave signal, and we can only measure one particular combination of the spins of the black holes projected onto their own orbital angular momentum. And this is called the effective spin. It's called this effective spin parameter, chi effective. And this shows 2 different estimations of the effective spins of these LIGO Virgo black holes from 2 different analyses. And the only difference between these 2 analyses is that they use different kind of priors for these effective spin. And here, these we call violent plots are the probability distributions of the posteriors of these parameters. If these violents are thicker, it means the probability is larger. If these violents are thinner, it means the probability is smaller. So you can see that according to the standard LIGO analysis, all of these have very weak spins, effective spin. They are very close to 0. And here is an independent analysis from the IAS group. And here they see some rather highly spinning objects. There's some with high spins, small spins, etc. The reason is that here they used a prior in the effective spin that is flat in effective spin. It's uniform in effective spin. While in this analysis, basically assume that this whole distribution of spin vectors has an isotropic angular distribution and a uniform magnitude distribution. So that would induce a certain kind of prior here, which gives you a larger support at chi effective close to 0. So this choice of priors can result in different measurements, and we will have to wait and see which one of these is actually closer to the nature. And one can also, so I said earlier that eventually these effective priors could be reduced because one could combine a large number of measurements, or this measurements will give you more and more confidence. And here is one example of how one would minimize the effect of priors as well as the uncertainty in estimating parameters if you have repeated measurement of the same thing. And here, what this shows, for example, the first measurement of the Hubble constant, which describes the expansion of the local universe, using the multi-messenger observation of the neutron star merger GW170817. So this shows, this blue distribution shows the distribution of a Hubble constant, the positive distribution Hubble constant from the gravitational observation. And you can see it's a very wide distribution. In fact, current measurements are much better using CMB and supernovae, so we are nowhere close to that. And this shows, for example, a projection of the future measurements using future observations of gravitational waves. It shows how multiple observations of Hubble constant from a large number of such measurements, neutron star measurements, each being not very precise, but when you can combine them, this combined posterior becomes much more precise and much more narrow. So each of these colored distributions are, one measured or one future measurement that one will anticipate. And when you combine these future measurements, you get a much more accurate and precise estimate of the Hubble constant. So it shows how you can combine multiple measurements to improve the posterior of common parameters. One could also ask, if you observe a large number of individual black holes, how can you say something about the population properties of these black holes? What is their mass distribution? How are these mergers distributed in cosmological redshift? Does it follow the star formation rate, or is it for something else? So there's a nice way of doing it in a hierarchical way, again, in a totally Bayesian way. So here, the idea that your hypothesis is that there is some model of the mass and redshift distribution of this binary black hole. And it has a set of parameters called alpha. So a choice of alpha will give you an astrophysical model, and it gives you a given distribution of the masses, spins, their redshifts, etc. And so there's a conditional prior here. So a given model parameter alpha will give you a set of a distribution of the parameters theta, which are the mass of the individual events, their spins, their redshift distribution, etc. And then from each event n, dn, we can compute the likelihood of this set of parameters. And if you marginalize it over this intrinsic parameter of the events, you can compute a likelihood of the alpha given the data. So you're asking, given the data dn, given the nth event, what is the marginal likelihood of this hyperparameter, which is describing the model of the population of binary black holes? And then you have multiple events. You can combine these marginal likelihoods from n different events. And you can ask, given the set of events, which are describe data of the nth event, what is the parameter, distribution of parameters that describe the population properties of binary black holes? And events also have to factor in things like selection effects, etc. I won't go to that detail, but one has to exercise care. But here's one example of how one does that. So here, for example, the left plot here shows the observed mass of the primary black hole and the mass ratio, the M1 by M2, or M2 by N1 of binary black holes observed using, I think, the second observing round of LIGO. And each of these blue contours shows one particular observed signal. And by combining this, we are able to reconstruct the population distribution of the mass of the black holes in the universe. So it's a very imprecise distribution. So you can see that it follows roughly some kind of a power law, but we do have some measurement of, we have some understanding of how the binary black hole masses are distributed in the universe. It follows a power law like this with some additional possible features. And this shows how, for example, how the mass ratio of these black holes are distributed. Most of them have equal masses, and the number of black holes with large mass ratio is small. So it shows an example of how one could do population inference. One could extract properties of the population of black holes, population of the astrophysical sources, using the observed events. One can also, if you have multiple hypotheses explaining the signal, one could also rank the evidence of these hypotheses. So one, for example, our basic assumption is that in all of these observations and calculations, the theory of general relativity is the right theory of gravity. However, there are alternative theories of gravity, which make similar kind of predictions, but they differ slightly. So one could ask the question, given the data D, what is the posterior probability of this alternative theory being the right theory versus the general theory of relativity being the right theory? So one can compute the Bayesian odds ratio between the two hypotheses. And using the Bayes theorem, we can split this into two, just like we did very early on in the detection problem, as a ratio of priors, it's called the prior odds, times the ratio of the likelihoods, which is called the likelihood ratio. Now, for example, we know that GR has been very well tested. GR has tested, basically passed all the observational tests and experimental tests with flying colors. So our prior odds for GR is pretty strong. So if you want to, if one certain observation want to claim that GR is wrong and some alternative theory is correct, it better has to have some very large likelihood ratio supporting this alternative theory. And how do you compute this likelihood ratio? So you have certain parameters for this theory, theta, and basically you can marginalize your likelihood of that parameter, that theory over the parameters theory. And like what we did earlier. So here is a study that shows how one could possibly detect two different models of the polarization content of the gravitational waves. So let me take one step back. So we showed yesterday, and also we reviewed today, that gravitational waves have only two independent polarizations. So there are only the H plus and H cross component that are independent in the metric perturbation. But there are alternative theories of gravity that predicts non-zero values for other polarization modes also. There are theories predict 10, these two modes that we see in H plus in GR are the tensor modes. They introduce quadrupole type deformations in the string of test particles. But there are theories predict dipole type polarizations and monopole type polarizations, scalar modes also. And this, for example, so that would change the polarization of gravitational waves, and one could potentially measure it using a network of interferometers. And this, for example, shows how one could compute this likelihood ratio, the Bayes factor between the two hypotheses, an alternative hypothesis and the GR hypothesis, and how one could distinguish. It shows a distribution of the Bayes factors when the data is actually purely GR. How well can you rule out this alternative theory, or how large is the likelihood ratio? The details are not important, but it shows an illustration of how one could do a Bayesian model selection. So these are the summary of the standard methods that one could apply in the gravitational wave analysis. And in the next 10 minutes, I will also give you a glimpse of some of the more real life problems, because so far we have idealized everything as stationary Gaussian noise and developed a formalism based on those assumptions. It turns out that the data are not exactly Gaussian. There are some non-Gaussian tails. If you look at the distribution of the samples of the LIGO Virgo data, they're mostly distributed according to Gaussian distribution, but they are non-Gaussian tails. And if you compute like a match filter statistics, then if they were Gaussian noise, then the distribution of this inner product would follow a particular distribution, like a chi-square distribution. So there's it would have a very rapid fall off like this, like this CN curve. But when you actually do that, you get something like this black distribution. You see some events with very large values of this chi-square, which you don't expect from pure Gaussian noise. So one has to develop some methods to clean the data from these non-Gaussian kind of transient that are actually there in the data. And there are multiple things that one has to do. One is, a popular technique is called the so-called chi-square test, where you're just not only looking at this inner product of the data template, but also looking at the integrand of the inner product, how the contribution to the inner product is changing as a function of the frequency. So basically, whether the frequency distribution of the data is consistent with the frequency distribution that we expect from signal. So you can, it's called a chi-square test. And if the data is actually truly following a signal, then the chi-square should have a small value. If not, it will have a high value. So one could use it to distinguish between true events and false events. Another idea is that you record a large number of environmental and instrumental monitors, because it's a very complex instrument. It's affected by both environment as well as various instrumental artifacts. But these are being recorded, like seismic noise and acoustic sensors and magnetometer sensors and laser frequency fluctuation. All these are not as recorded in LIGO and Virgo. And one could check whether a particular feature in the gravitational wave channel is contributed by any of these instrumental artifacts. And it's called auxiliary channel vetoes. And there are a number of such auxiliary channels are used to veto out the bad part of data. Another most powerful technique is to require that the true gravitational waves be coincident in multiple detectors. Because if the signal is a truly gravitational wave, it has to be detected by multiple detectors. But if it's an instrumental artifact, it's very likely that you will have the same kind of instrumental artifact occurring at the same time in multiple detectors that are separated by thousands of kilometers. This will also help you distinguish between true events and false events to a very good extent. So all these are used to weed out these false events. Still, one would have some fake signals mimicking true signals. So you already have some sort of background distribution of noise events. So we are coming back to the question of how do you get a threshold on this, whatever statistic that we are doing, so that what kind of confidence that we can associate with a given detection. And for example, it's a very common problem in any signal detection. For example, if you have a photon detector like a telescope, you also have a probability that even in the absence of any photons hitting this CCD camera, you will have some dark photons. And you can calibrate this instrument by basically closing the telescope. You just put on the hood and you measure the dark current, the number of dark photons the electrons coming out of this dark photon, this dark current. And that dark current is estimated and measured. You require that the true, if you want to claim some fluxus detection, the number count has to be greater than this dark experiential dark current. Unfortunately, you cannot do it in gravitational detectors because you cannot shield the gravitational waves. They would penetrate through everything. So what you do is something interestingly and clever. If you have multiple detectors, you can do something very clever. If there are multiple detectors, since you know the distance between them very, very precisely, and you know the precise velocity of propagation of gravitational waves, it means that they have to arrive, the same signal has to arrive at the two detectors within some delayed time. So if you see two signals that are more delayed than the light travel time between two detectors, they cannot be gravitational waves, right? So while things like instrumental artifacts, they are happening at the instruments at certain statistical, some random processes, they have some properties, and they would be coincident with some random times also. So what you do is you apply a time shift between the two data streams, between two detectors, and the time shift is larger than the light travel time between two detectors, or gravitational wave travel time between two detectors, so that these coincident triggers in the time lag cannot be true gravitational waves. So you count the number of coincidences between these time lagged analysis, and you build a distribution of this detection statistic. And that is shown, for example, by these black histograms. This shows from the first observing round how we expect the background events to be distributed like this. So the probability of getting a value of this detection statistic that is 20 is extremely small. That probability is like 10 to the minus 5. And here shows one event. This is the very first gravitational event. So it shows that it's very extremely unlikely that the noise would mimic a signal like this. So it's a very, very significant event. That probability for a false event mimicking the signal is like less than 10 to the minus 7 or so. So it's a 5 sigma discovery. That's how you estimate the background. So far, I've been only talking about the detection and analysis of model signals, well-modeled signals, because it requires matching the data with theoretical models of the expected signals. And that works very well for things like compact binaries. But we also expect, as we discussed yesterday, other kinds of sources, the supernovae, which are not very well modeled, but they have a property, expected property, that they produce some very short bursts of gravitational radiation. So here is a cartoon. So we have some data, and suddenly we expect some sort of a burst. So you could do some very simple, excess power algorithm. The idea that you compute some mean variance of the data, that's something like here, and you set a threshold such that it is several times the mean variance, and you have to, if you see an event in the data which is significantly louder than these threshold, you can claim a detection. And one can improve it just without doing a simple time domain excess power. One could do a time frequency decomposition of the data. So here, for example, shows a spectrogram of the data. So here is the time, and the vertical axis shows Fourier transforms of short segments of data. And this shows, for example, you have a fake signal. I've created a fake data containing a signal that has a very nice excess power that is localized to some short milliseconds, about at around 4 seconds, and it is localized to about a few hertz. So one could do a version of a time frequency excess power. One could also use some wavelet transformations. So this is a Fourier decomposition of data, because one could come up with some sort of wavelet that would look like potential signal that would look for, like this kind of what is called a sine Gaussian signal. Here is a burst of radiation, which is corresponding to a particular frequency and some damping time. And one could decompose the data into wavelets. And here is a wavelet decomposition of the data containing a true signal. And you can see this very nice chirping signal that is looking like this. So you have a gravitational wave going upwards in frequency and having a bright power. So it's again another way of detecting such excess power of the data using a clever wavelet decomposition. There are and if you have multiple detectors, one could also use properties of the expected properties of gravitational waves, and one could basically coherently combine the data to enhance the signal noise ratio. One could also do some clever techniques. For example, if you have 3 misaligned detectors, we are actually, in each detector is measuring one particular combination of H plus and H cross. You have only 2 independent degrees of freedom, independent polarizations, H plus and H cross. And each detector is measuring one particular combination of H plus and H cross. And if you have 3 different measurements, and if you have 2 different measurements, you can independently construct H plus and H cross. albeit the presence of noise, there is some uncertainty there. And if you have a third detector, you have a consistency check, because you can check whether the third detector is actually consistent with what we observe from the first two detectors. So you can create, since you can reconstruct the H plus and H cross from the first two detectors, you can predict the combination of the data of the polarization that would appear in the third detector, and you could subtract it. So you could compute a particular linear combination of the observed data from the T detectors in which the signal should be absent by construction. So it's called a null stream. So if you have a true signal, basically you can combine one particular coherent additional signal in which the signal to noise ratio should be the largest, and a null stream in which the signal power should be the weakest. So these two things can be used to distinguish between true events and false events also. The remaining 2 slides, I will very briefly describe the data analysis for detecting the 2 other kinds of sources. One is, sources of continuous gravitational waves, such as rapidly spinning neutron stars. I mentioned yesterday that basically they produce weak sine wave like gravitational waves that would have a remarkably same frequency over a long time. The frequency will only change time scales of years or very slowly. And basically one can, so if you have only a pure sine wave, the best way to detect that signal is you just compute a Fourier transfer data. You take a very long in a segment like 1 year of data, you compute one Fourier transform. And if that has a signal of 100 hertz, you would see a peak in the Fourier transform. But unfortunately, it's not that simple in here, because during this 1 year, the Earth would be rotating several times around its axis every day. And the Earth would rotate around the sun once in this 1 year. And this motion of the Earth related to a distant source would create Doppler modulations in the observed signal. And that would depend precisely on the location of the source. So one has to basically account for this Doppler modulation, and you can compute a match filter that would include this Doppler modulation. And with that, one can integrate the signal for very long time, like months and possibly years. It's a very computationally expensive problem, but it can be done for some non-sources of non-spinning neutron stars, like radio pulsars that we know because we know their location in the sky, we know their spin frequency, etc., which would reduce the complexity of the searches. But for we also know that we only know a small fraction of the neutron stars in the galaxy as radio pulsars. There are possibly 1 billion neutron stars in the galaxy, and possibly or even 100 million at least. And we don't know them as pulsars. So one also needs to do some sort of blind searches to look for everywhere. But for that, one has to use some kind of semi-coherent methods, which are not as sensitive to as this. So there is a very nice review, a living review by Keith Riles, recently come out last year. So if you're interested in the details, I would encourage you to take a look at that living reviews. And finally, the detection of the stochastic gravitational wave background. Here, unlike any of the sources that I mentioned earlier, the signals themselves look like noise. They look like stochastic processes. So one cannot do any kind of technique that we described earlier. However, one can still utilize the property that even though this signal is noise-like, they're stochastic, you should see the same signal in multiple detectors. So one can actually cross-correlate the data between multiple detectors, and the noise would cancel out, but the signal would amplify it. That is the technique of the stochastic gravitational searches. One has to be a bit careful here, because the cross-correlation would actually depend on the arrival direction from the sky, and the stochastic gravitational waves are coming from all directions. So one has to do a sky average quantity. And it turns out that if your frequency, in certain conditions, the the correlations would actually cancel out. So one has to compute a certain quantity called the overlap reduction function between two detectors to see if it's appropriate to do, stochastic gravitational searches between two detectors. So far, it's only done between LIGO, the two detectors LIGO only, because that is the best that one could do. Here also, I have not mentioned any detail. There's a nice living review by Romano and sorry, I'm blanking on my name. But there's a nice living review by Romano in Joe Romano in this in the living review relativity, which contains a lot of very nice pedagogical introduction, as well as research content on the search for stochastic gravitational wave background. And so that's all for today. Tomorrow I will give you a summary of the current status of gravitational observations and the prospect for near future. Let me stop here, and thank you very much. And so this living review that I talked about was Cornish and Romano. Neil Cornish and John Romano has a very nice review on the sources and searches for stochastic gravitational background.